Hello friends, today we will learn linear programming method to solve rectangular games. So let us consider an M cross N payoff matrix to player A like this. Player A this side, player B this side, and these are the strategies of player A, A1, A2 up to AM, and the strategies of player B are B1, B2, Bn, and these values are the corresponding payoff values A11, A12, A1n, and so on. Okay. Now, assuming that this game doesn't possess any saddle point, okay, so we will try to obtain the optimal mix strategies. So let SA is equal to A1, A2, AM, P1, P2, PM like this. That is, player A selects your strategy A1 with probability P1, strategy A2 with probability P2, and strategy AM with probability PM, where sum of all these probabilities is equal to 1. And SB, again the optimal mix strategy to player B. So B1, Q1, B2, Q2, B and Qn. So these are the respective probabilities of choosing the strategies B1, B2 and Bn, where P summation over J, Qj is equal to 1. That is, sum of probabilities is equal to 1. Then the expected gains Gg of player A against B's pure strategies will be equal to Gj is equal to summation I from 1 to M Aij Pi j running from 1 to n. For example, if we simply put j is equal to 1, so we will get g1. Okay, so g1 will be equal to summation I from 1 to m ai1, okay, ai1 pi. Okay, so this will give me the expected payoff to player A, okay, corresponding to the pure strategy B1 of player B, and the expected losses Li of player B against A's pure strategies will be, okay, so these are denoted by Li, and again these are equal to j from 1 to n Aij Qj, where I runs from 1 to m. Okay. The objective of player A is to select AIs with probability PIs, that is I from 1 to m, such that he can maximize his minimum expected gains. So let U is equal to minimum of the gains, okay, expected gains of player A against B's pure strategies. So it is denoted by this minimum of this we have known in the previous slide. So minimum of this, let that be U, okay, therefore U is equal to minimum of, let us denote these values by G1, G2 and Gn. Then player A likes to maximize U, that is the minimum expected gains. Okay, so for player A, the problem can be written as a linear programming problem like this, with the objective function maximize U, means maximize of whatever we have written earlier, that is minimum over j summation I from 1 to m aij pi. Subject to the constraints. Now what are the constraints? Since this U is minimum of this summation over I, aij_pi. Therefore, the summation over I from 1 to m aij_pi will be greater than equal to u. And sum of probabilities is 1 and pi greater than equal to 0. Okay, so this is the corresponding linear programming problem for player A. Similarly, the objective of player B is to minimize his maximum expected losses. He will select BJ's or QJ's, okay, J from 1 to n, so that his maximum expected loss is minimum, right? So let V equal to maximum over I summation over J from 1 to n aij qj. Okay, that is V is equal to maximum over I, L1, L2, Lm. These are the corresponding losses. Then the player B wishes to minimize V, that is maximum possible losses, maximum expected losses to him. Okay, so for player B, the problem becomes minimize V, that is minimize or maximum expected losses subject to the constraints summation over G from 1 to n aij qj less than equal to V. Because V is the maximum of this, so definitely this expression summation J from 1 to n aij qj will be less than equal to V. And summation over G from 1 to n qj is equal to 1. The sum of probabilities is equal to 1 and qj definitely greater than equal to 0. Probabilities cannot be negative. Now it is easy to note that the linear programming problems of two players represent a primal dual pair. It's quite easy to see, see the problem of this player is its objective function is minimization type, and the objective function of player A is of maximization type. And here again, this all the constraints of greater than equal to type, all the constraints of less than equal to type, and all that. So we can see that these LPPs of player A and player B form a primal dual pair. And once it is known to us, therefore by fundamental theorem of duality, one can read the optimal solution of one player just from the optimal simplex table of the other player's LPP. That is, we need to solve the LPP of one player only, and we will focus on that LPP where only slack variables are required, right? So further we can write those two LPPs like this, that maximize U is just like minimizing 1 upon U, and for 1 we can write summation over Pi, because summation Pi equal to 1. So just writing this way and minimize summation over I Pi upon U, and let us consider Pi upon U is denoted by Xi. So it is minimize summation over Ixi, or simply minimize 1 upon U is equal to x1 plus x2 and xm, such that summation over I from 1 to m aijxi greater than equal to 1. So what we did, we simply divided both sides y u, and then this Pi upon U is Xi, so it is written over here, and definitely get the B upon B1, so greater than equal to 1, and Xi greater than equal to 0 because of this, because Pi is always positive, U is also positive, and therefore Xi is greater than equal to 0, or we can write summation I from 1 to m Pi equal to 1 and Pi greater than equal to 0. Similarly, we can write the linear programming for player B like this: minimize, so V is just like maximizing 1 upon V, and like this: summation over G from 1 to n Qj is equal to 1, and that's why we have written this. And let us suppose that Qj upon V is equal to Yj, so it is maximize summation over J Yj, or simply maximize 1 upon V is Y1 plus Y2 plus Yn, such that these are the constraints. So just dividing both sides by V in the previous LPP, so that will become Aij Qj upon V, and that is Yj here, and V upon V1, and Yj greater than equal to 0. So these are the LPPs of both the players of this game, and we can solve definitely player B's LPP because it's of maximization type and all the constraints of less than equal to type. And from the solution of this LPP, one can read the solution of the other using the fundamental principle of duality. So this way the matrix games can be solved with the help of linear programming method. There is one note: linear programming technique requires all variables to be non-negative, and therefore to obtain a non-negative value of the game, the data to the problem, that is Aij's in the payoff table, should be non-negative. If there are some negative elements in the payoff table or matrix, a constant to every element in the payoff table must be added so as to make the smallest element 0. The solution to this game, that is new game now, whenever you added this constant, will give an optimal mix strategy. So solve that, and the values of Yj's can be obtained, and from those we can find out the values of Qj's. So an optimal mix strategy to player B can be obtained, or to player A we can also obtain. Okay, that is for original game. Whatever we get, that is for original game. But however, the value of original game will be equal to the value of the new game minus the constant added. Okay, so whatever value you get, because from duality we know minimize u is equal to maximize u. Minimize u is equal to maximize v, means the optimal values of both the problems are same. Okay, and then we can have the value, whatever value we get, that will be the value of the game. Okay, so from that value we have to subtract the constant that we have added in the table in order to get the value of the original game. However, the optimal strategies will be obtained as it is. For example, if you consider this game, player A and player B, these are the strategy of player A, these are strategy of player B. We can see that there are certain negative elements in this table. So what we have to do, we have to add some constants. Let us add 4 to every element so that these elements become like this. 4 plus 1, 5, 4 minus 1, 3, and like this. So all the elements are positive now. And at the end of the solution, whenever you get, suppose, when we solve this, we get the value of the game as 5, v as 5. So therefore the value of original game will be 5 minus 4, the constant added, that is equal to 1. Okay. So in the next class, we are going to solve a numerical example based on this matrix method for solving the matrix games, and everything will be very clear that how do we write the solution of solution to the other player from the optimal solution of LPP of one player. So thank you very much.